Hello, everyone, and welcome back to Tiny Potato Studio Productions. We are now in our third lesson online for Psychology 300, and this is a pretty big day. This is analysis of variance. It fits into one kind of beefy lecture, and that's fine. Even though it's a fairly big concept and a very useful procedure, the mathematics around it are relatively straightforward, and it is a nice, juicy, multi-step procedure, algorithm that a lot of students, after having dealt with the concept of power and the concept of different types of measurement scales and the concept of this and the concept of that, find a lot of comfort in. This is a procedure. This is an algorithm. Um, Speaking of power, here's a bit of good news that I think I neglected to share with you while we were covering it. When it comes time to ask you questions about the concept of statistical power, beta, 1 minus beta, type 2 error, that kind of stuff, I keep my questions to the conceptual and not the calculated, not the mathematical. So if you think back to the in-class assignment number 7 that we had last week, everything from the front page is the kind of thing that you can expect to see on the exam. The calculations and the sorting out which area of the curve equals what number on the back page, where people had the most trouble, is not something that I put on either the final or the upcoming exam. I have tried to do that in the past. It never resulted in a large enough proportion of people getting it right for it to really be worth including in the test, and so I've changed my strategy. So hopefully that's good news. Pay attention, focus. There will be questions about it, but it will all be stuff that is similar to the front page of the in-class assignment. All right, let's get to ANOVA. ANOVA stands for Analysis of Variance. And if you think about it, we've been analyzing variance for quite some time now. We just haven't called it ANOVA. So while ANOVA might look a lot different from what we've done before, it's actually following a logic that should be very familiar to you. In all of the hypothesis testing that we've done so far, single sample, related samples, and independent samples, what we've always been doing is figuring out what kind of difference the statistic that we've pulled with all of its sampling error and with all of its noise, what story that statistic has told about the difference we're looking for, but then put it in perspective by figuring out how much error we should expect that statistic to be dragging along with it. So when we did a single sample, we pulled an X bar out of what is potentially a new population and compared it to the mu of the old population to see how much difference there was there. A lot of difference means that there's probably something there to report. But what a lot of difference means is a lot of difference relative to the standard error, which we had to calculate. In related samples test, we saw if that D bar, that average difference score, was big compared to 0, but we had to take into account how much error was going into those difference scores. So if there was a very large or very small, very positive or very negative average difference score relative to the S sub D bar, then we had a significant hypothesis test. Probably the most intuitive example of this was in the independent samples test. You had a mean from one population, you had a mean from another population, and if the difference between those means was big, you might think you had something. Hey, that mean and this other mean, they've created a big difference, but you don't know whether that difference is actually worth paying attention to unless you figured out how much error was associated with those statistics. So when we finally got a test ratio for the independent samples test, it was X bar sub 1 minus X bar sub 2, and you saw if that was big relative to S sub X bar sub 1 minus X bar sub 2, the standard error. All right, so that is exactly what we are going to be doing with ANOVA. In every case, when you run a hypothesis test, you are concerned with the size of the observed effect among the statistics divided by the amount of error that is expected to be in those statistics. And at the end, you ask the question, is the effect we've seen big enough to be considered real given how much error there is likely to be? That is the decision at the end of a hypothesis test to see whether you accept or reject the null hypothesis. Analysis of variance is the exact same concept, but now applied to 3 or more groups. When you did an independent samples t-test, it was one group and another group. You saw the difference. For ANOVA, it's one group and another group and another group. And what you want to do is to figure out how much difference there is between all the groups instead of just one distance between two groups, okay? So we've got a method to do that. We've got a way to figure out how much groups are close together or how much groups are separated from each other. And we'll run through the math on that. But at the end of the day, we'll see how much separation there is among the means of these groups and then compare it to how much noise or how much statistical error we can expect to come from this procedure. So in the ANOVA, the size of the effect, the numerator in that test ratio is how much the group means differ from each other, as I said. The bottom, the denominator, what we've always been calling the standard error, is going to be calculated by figuring out how much variance, how much difference there is within the groups that we are talking about. Now, when we did S sub x bar sub 1 minus x bar sub 2, we were doing this as well. That number became big when S sub 1 and S sub 2 were big, but we just did a weighted average of those to figure out how much error we should expect. ANOVA is gonna be pretty much the same thing, but it relies on this very particular insight, which is this. If you have one group and another group and another group, what we are talking about in an ANOVA is that the only really relevant factor, the only relevant piece of information about the people in a group is the group that they are in. So for instance, we had people who got 6 hours of sleep, people who get 8 hours of sleep, and people who get 10 hours of sleep. The people getting 6 hours of sleep might be very different from each other. Some are male, some are female, some are non-binary, some of them drink a lot of caffeine, some don't drink a lot of caffeine, and they probably all have individual sleep needs that reflect how good 6 hours of sleep is going to do for them when it comes time to test them on something like cognitive function or ability to memorize or ability to take a test or pay attention for a long time to a screen. 6 hours of sleep is going to affect each one of those people in that group differently. But when it comes to the math, when it comes to the statistics, the only relevant piece of information about every single person in the 6 hour group is that they're in the 6 hour group. So except for sampling error, these are all 6 hour group people. So the fact that some are male, some are female, some drink coffee, some don't, some are affected by 6 hours differently than other people, that all goes into the sampling error concept, which means this. The only reason that any member of one group in an ANOVA differs from another member of the same group in an ANOVA is sampling error. If there were no sampling error, every single person in that group would give you the exact same reading, would give you the exact same measurement. So if we have a way to figure out how much the people within the group and the people within the group and the people within the group differ from each other, we will get a useful number in terms of how much standard error we can expect. All right? So that then becomes our test ratio. Our test ratio this time is not a T, it's not a Z. There's a new statistic in town. It is F. This is going to be the F ratio. So we're going to figure out how much difference there is between the groups. Then we're going to figure out how much difference there is between the members within each group, and we'll make a ratio out of that. Okay? That's all there is to it. The devil's in the details. Exactly how do we get the number for the top and the number for the bottom that we can then put into a ratio, and that's what the rest of the lecture is all about. All right? So in order to do that, we're going to need a few concepts in our bag of tricks that we can use later on to figure out what's going on. The first one is the grand mean. The grand mean is what happens when you throw every member from every group all in one at the same time and just take an average of everybody. It is the mean of everybody regardless of group. In addition to that, there are group means or sample means, which is to say, as many different groups as you have that you're comparing to each other, you have a mean for each group. Okay, this is getting impossible to talk about unless I anchor it to some sort of example. And so here's the made-up example that I've got for you. There is discussion among people in academia as to whether or not it is appropriate to give people tests on different colored paper. Not gonna lie, this is true. And the idea is that there's a real difference in performance based on how different colors make people feel, and how difficult it is to read printing on different color paper. So what I've done here is I've given 4 different groups 4 different colors of paper. As you can see down here, 10 people got blue paper, 10 people got red paper, 10 people got green paper, and just to make it interesting, 7 people got purple paper. What I needed to do then was give everybody some sort of measurement on this paper and then get a reading for them based on how they did on this measurement, and then keep track of what color paper they had. So I did a memory test. Okay, you could score anywhere between 1 and 10 with fractions possible on this memory test, so that people who were taking blue paper got an average, in those 10 people, got an average of 7.9 on the memory test. People on the red paper got an average of 5.79 on the memory test. People on the green paper got an average of 8.83, and people on the purple paper got an average of 6.03. That means that there were 37 people in this entire study, 10 in 3 groups and 7 in the last group, for a grand total of 37. If you added up everybody's score, all 37 scores, and divided by 37, you would have gotten a grand mean of 7.23. So it's going to be very important for us to keep track of which one of these groups we're talking about. And so it's important to subscript it with blue, red, green, purple, and grand mean. All right? So now that that's our setup, let me tell you about what the null hypothesis means and what the alternative hypotheses mean. In an ANOVA, the null hypothesis is that across the board, we don't have enough evidence to suggest that any group is different from any other group, which is to say, for all we know, the mu of the blue population is exactly equal to the mu of red, green, and purple populations. If even one of these populations is so different from the other ones as to produce an X bar that creates a separation big enough for us to declare the ANOVA to be significant, then it will be significant. The null hypothesis will be false. Now, it could be that they're all very different from each other. It could be that 3 are close together and one's way off in the corner. We have no way of differentiating that until after the test is done. So the null hypothesis just means that we're equal across the board, and everything that isn't equality across the board is wrapped up into the alternative hypothesis. So that's why I haven't written an alternative hypothesis down here. The alternative hypothesis is just that there is some inequality somewhere in the null hypothesis. Since it's not easy to state, we don't bother to write it down. There are so many different possibilities that it's pointless to list them all right? But the point is that the ANOVA is a test of the overall model of equality. So let's go ahead and get started. Let's work the example. Let's start with our raw data. These are 10 people who took the test on blue paper, 10 people who took the test on red paper, 10 people who took the test on green paper, and 7 people who took the test on purple paper. The average for blue, the average for green, the average for red, and the average for purple, and there's the grand mean. All right, so as I've said before, in order to get our ratio, we need the within group differences, and we need the between group differences. Let's see how it is that we can get them. Now, we've talked about several different ways to measure the amount of difference between numbers in a list. Okay, we can take the range, we can take the sum of squares, we can take the variance, Usually, typically, we use the standard deviation. It turns out that if you want a number that is malleable to be manipulated in terms of dividing it and multiplying it and adding it together, the level of calculation that lets you do all that stuff without running into bias and errors is variance. I'm not going to explain exactly why, but it turns out that that is the case. Variance is the thing that is flexible enough to add, multiply, subtract, and divide. Okay, so what we're going to do is we're going to stick with that step of the procedure in getting a standard deviation that stops short of getting a standard deviation and becomes just variance. Remember, variance is the second to last step before you take the square root and get a standard deviation. All right. But the step before that is getting the sum of squares. When you get the sum of squares, you put it over the degrees of freedom, you get the variance. So what we're going to need to do then is get a sum of squares for the measurements within our groups, and we'll need a sum of squares for the measurement between the means of our groups. Let's start with within, because it is by far the thing that is the most intimidating looking, even though it's just a repetitive, simple step done many, many times. Okay? Sum of squares for the error term, the denominator, those differences within a group, is about all the variation that we can see in this study that is due only to sampling error. None of these variations can possibly be due to paper color. Paper color is the thing that we're looking for in order to prove that it has an effect. But we're not looking for the effect of paper color. We're looking just for the effect of sampling error. That means comparing one person to all the other people in their own group. Okay, but we don't need to do that just for one group. We need to do that for all of the groups in the study so that we can get an estimation of how much error there is in the entire study, the entire experiment. When we get that sum of squares for the entire experiment, we're going to call it sum of squares sub error, the error term sum of squares. So what we end up doing is taking the difference between every individual data point in this entire study and comparing it to the mean of its own group. We then square that value and add them all together. So we will have to do this little thing 37 times. But we've done this before. What we're really doing is the first part of a standard deviation calculation, but we're just doing it for each one of the four groups. You know how to get a sum of squares. You've had to do it again and again and again as we've gone through this class. So just do it. There's a sum of squares for the blue group. There's a sum of squares for the red group, a sum of squares for the green group, and a sum of squares for the purple group. If you just do that separately, like you already know how to do, then in order to get the sum of squares for the error term, otherwise known as sum of squares within, you just take all four of those sums of squares and add them together. That becomes the total sum of squares. It's that easy. All right? So what we get when we take each member of the blue group, let me go back here, okay? That is to say like 3.8 minus 7.9 squared and added to 7.1 minus 7.9 squared plus 9.6 minus 7.9 squared. If you do that all 10 times and add them up, you get 51.98. If you do the same thing for red, you get 20.39, for green 50.59, and for purple 53.33. These are the sums of squares for each one of those groups. If you put them over the n minus 1 for each one of those groups, you would have variance for each group. And if you took the square root, you'd have the standard deviation for each group. But we don't want to do that. We want to add them all up as sums of squares first before we go on. So the total for those sums of squares is 179.29. If it is easy enough for you to follow along with proper mathematical notation, then everything that I have just said here on the slide is represented right here in this equation. Let me just point out the parts to you to see if you can follow along. All right, let's see. Sum of squares equals the sum of, and now there's these symbols up down here and up here. I is going to be the group that you are dealing with. So we're going to start with the first group. And we're going to do that for group 1, and then group 2, and then group 3, and then group 4, until we reach a value for I that is equal to K. K is the number of groups in the study. Since we have 4 groups in the study, K for us is equal to 4. So what this term says is that you're going to add the results from the first, second, third, and Kth group, which is 4. For each group, you're going to start with the first member of the group, that is J. J is the member of the group number. So you're going to start with the first member and say, oh, here's the reading for the first member. I'm going to subtract it from the mean of my ith group. In this case, it's the first group. I'm going to take that value, square it, and add it to whatever happens with the second member of that group, J equals 2. So the second member of the group minus the mean of the first group squared, add it to the da-da-da-da-da-da. For 3 of our groups, n up here of that group is 10. For the purple group, n of the 4th group, n sub 4, purple, is going to be 7. So you only do the 7 times. When you do all that and you add them all together, you will get this number, 179.29. This expression right here, sum of squares blue, red, green, purple, is another version of exactly this thing right here. But the thing to remember is K. K is the number of groups. That's going to come up again when we start talking about degrees of freedom. All right. So what's next? We now have a sum of squares for the error term, which was long and arduous and difficult. Now we want a sum of squares for the signal term, the numerator, the actual difference among our statistics. So what we're going to do there is, cleverly enough, we are going to treat each group mean as nothing more than one member of a data set that only has 4 values in it. So we're going to get the sum of squares among those 4 values. Well, how do we do that? Well, we got to compare them to some central value, and we're going to use the grand mean for that. All right. So you take each x bar, each mean for each group, you subtract it from the grand mean, square that value, weight it for how many people are in that group. We're going to have to do that really carefully. We'll talk about that in a second. And then add them all together to get a sum of squares between. All right. So what we're doing is we are summing up each data point in each group by how much they are creating difference between that group's mean and the grand mean. Let's see how that actually works in practice. So the sum of squares between is going to be this. There were 10 people in the blue group. The blue group had an average of 7.9, and the grand mean was 7.23. So what we're interested in is the difference between the blue mean and the grand mean, right here, see that? Squared, but here's the kicker. We have to weight that squared value by how many people were contributing in that group, okay? That keeps everything even. That makes sure that every data point is accounted for. Because remember, when we did the sum of squares within, we did 37 different procedures and then summed them all up into one term. Here, we got to make sure that all 37 of those points are also accounted for. So we multiply each result by how many data points were in that mean. Understanding it will help you remember, but memorizing it, if you can, will get you through. So here's what we have to do. For the red group, again, there were 10 people. The mean was 5.79. The grand mean is, as always, 7.23. So 5.79 minus 7.23 squared, but up. Once you square that value, you then multiply it by 10 because there were 10 people in the red group. Same for green. Here's purple. The average was 6.03. The grand mean is 7.23. You get that difference. You square it, and then you multiply it by 7 because there were 7 people in the purple group. Please make sure to get your order of operations correct here. You want to subtract the 2 values, square them, then multiply by how many people were in the group. You're going to get weird, wacky, humongous numbers if you take the difference, multiply it by n, and then square it. So make sure you get your orders of operations right. Okay? In this example, though, if you did all that correctly, you would get a sum of squares term in the numerator of 60.88. In terms for the math geeks might enjoy. For the first group, I equals 1, that is n of I, n of 1 in this case, it was 10. You take the average of that first group, you subtract the grand mean, square it, multiply it by how many people were in that group, and then add that to the next result, the next result, the next result, until you hit K, the number of groups. All right? So take a step back, take a breather, and talk about what we've done so far. Analysis of variance is a ratio of effect to error. The effect in an ANOVA is the amount of difference between the means of your groups. We are going to calculate the variance between groups. So far, all we have is the sum of squares. The error term in an ANOVA is the amount of difference between members of the same group. We've gotten a summed up term right now. It is the sum of squared differences for the error term, and that is now sum of squares within, also known as sum of squared error. We have sums of squares. Remember though, a sum of squares doesn't become a variance until you divide it by the degrees of freedom. So we got to figure out what degrees of freedom we're going to be dealing with. In order to cut the sum of squares back down to size, we have to figure out how many data points contributed to each sum of squares. All right. There were a lot of parameters that we estimated here. We lose a degree of freedom for each parameter. That means 4 degrees of freedom between, that is to say, the difference between the means of each group, we were estimating the standard deviation of those 4 groups relative to the grand mean. And so we only had K data points, really, 4 groups. So we're going to lose 1 degree of freedom from those 4 groups. That means that the degree of freedom between, on the top in the numerator, is K minus 1. In this instance, in this example, it's going to be 4 minus 1 or equal to 3. So when we have the sum of squares between, we divide that by 3 to get our variance between. 4 degrees of freedom within. We had a different parameter sigma for each one of the 4 groups, but we had 37 people contributing to figuring out what those sigmas were. So in that case, we get to take all 37 people, but subtract 1 for each group that we were dealing with. That means big N minus K. Big N here is meaningfully different from small n that we usually use. Big N means the grand total number of people that are contributing to the entire study across the board. Okay? So degrees of freedom within is big N minus K. Putting that all together, we can put the sum of squares over the degrees of freedom every time to make an average of square deviations, otherwise known as a variance. That's why, for reasons that I will never be able to understand, they decided to stop using the perfectly good word variance, which is even in the title of the damn thing, analysis of variance, but instead come up with a new term that means exactly the same thing as variance, because you have taken the mean, in a sense, the degrees of freedom is our divisor to get a mean of the sum of squares. They now start calling variance in this equation a mean square. Okay? So when you take the sum of squares between and you put it over the degrees of freedom between to kind of get a mean amount of difference that you're working with, that's no longer called a variance, that's called a mean square. Mean square between. Same thing for within. You take the sum of squares that you had within, you put it over the degrees of freedom within, and now you have the mean squared within. Within, being the error term, can also be called mean squared error. This leads us to the absurd statement that variance within is the same as variance error, is the same as mean squared within, is the same as mean squared error. All 4 of those terms mean exactly the same thing without nuance. There are no shades of meaning there. All of them mean the same thing. By the time you get to talking to other statisticians, by the time you get talking in SPSS, mean squared error becomes the preferred term. All right? Sorry about that. I didn't make this up. For between groups then, and within groups, you've got mean squared between being sum of squares between divided by degrees of freedom between. That means whatever sum of squares between we had divided by k minus 1, that 60.88 was the sum of squares between from a slide or two ago, divided by 3 gives us a variance or a mean square for the numerator, the signal term, the actual difference of 20.29. That's how much differentiation we have between our means. That number has to be big relative to the error term in order for us to have statistical significance. Okay? So that is, we have to know that ratio of signal to noise. We've got the numerator term now, all right? We need our error term. So in ANOVA, the error term is variance within, and that is mean squared, sum of squares within divided by degrees of freedom within to give us mean squared error. In this case, that was 5.43, right? So that's right here. Mean square within equals sum of squares within divided by degrees of freedom within, which is 179.29 divided by 37 people in the study minus 4 groups, 5.43. Put those in a ratio, we get a 3.74. That is the F ratio. That is the test ratio. That is what T used to be. F equals 3.74. We have now boiled the entirety of our data set down to one number that expresses how much evidence we have versus how much noise we have. Okay? So what I'd like to do with you right now is to kind of share what it looks like to do an ANOVA in a way that might help you to understand what's happening. I always think of an ANOVA as like a bunch of stuff that is in a trash compactor. It gets crunched and it gets crunched again, and it ends up with one little cube that has everything in it that you started with, but is in a much more compact form. So what you start off with is the sum of squares between up here, and on the bottom, the sum of squares within. But that's in there with a lot of garbage. The degrees of freedom between, and here, the degrees of freedom within. That's 4 things. 2 up here, 2 down here. We got to simplify that. So when you do the math, you end up taking the top one and crunching it, and taking the bottom one and crunching it in order to get mean squared between. This is mean squared within. I'm going to do it properly and call it mean squared error. But that's still a divisor. It's still a division equation. It's still not one answer, one number. When you crunch it one more time, it just becomes F. Okay? So it's 4 things, crunched down to 2 things, crunched down to 1 thing. That's what we do with an ANOVA. Okay? So with that F statistic, it is a 3.74, but we still have no idea whether that's a lot. It could be a very small number. It could be a very large number. We don't know. We need to go, as usual, to a table to tell us whether a statistic is an appropriate ratio to get excited about. That then becomes our visit to the new table, which is the F table. The F table has, and this is going to be on your test, 3 things that you need to know in order to find the appropriate critical value off of your F table. The first is the alpha level. How confident do you have to be that an ANOVA is significant before you declare it to be significant? That will determine which F table you actually use. The one that we're using here is the F table for the 0.05 level of significance. So this entire table is only for use with an alpha of 0.05. In the T table, we had a column for 0.05. Now F, being more complicated, takes an entire page for 0.05. There's a 0.01 table, there's a 0.1 table, I'm sure, but we are right now using the 0.05 alpha table. Once you have the right table, you have the right sheet, your first bit of information has been used, you now have to figure out 2 more things. The degrees of freedom that you were dealing with between groups and the degrees of freedom that you were dealing with within groups. For us, since we had 4 groups, degrees of freedom between is 4 minus 1 equal to 3. So we're going to be using this column. For within, we had 37 people, but 4 groups. So 37 minus 4 was 33. We are going to be using then the row associated with those degrees of freedom. Now, there's not a row for every degree of freedom up to however big your sample size might be. After a certain amount of time, just like on the t-table, those start skipping down. Because we had 33 degrees of freedom, we want to use 30 degrees of freedom on the table in order to keep ourselves honest. Never round up. If we had 39 degrees of freedom, we would go back down to 30, not up to 40. Okay? It's just a way of keeping yourself honest. So, degrees of freedom between is 3. Degrees of freedom within is on this table 30. That gives you a 2.92 for the critical value on your F statistic. Our F statistic was 3.74. The critical value is 2.92, so you reject the null. You've actually got a statistically significant finding here. Here's a nice thing about ANOVA. Since everything at some point was squared, and all you're doing is taking divisors, you'll never get a negative. So you will never have a negative F value, and so you never have to worry about a negative in your critical values either. Okay. But what we can say then is, since we gave different color paper to different people in different groups, and we did a memory test on all those people, and we got a significant F statistic, we can say paper color had a significant effect on memory. Here are a couple of other different ways to say that. It is probably meaningful to classify performance on a memory test according to which color paper you took the test on. Now, that's certainly not the only factor that is going to be meaningful. The difficulty of the words, the amount of sleep the person had, how good they are generally at memory, how much time they had, whether there was noise in the room. Those are all factors. But one of the factors that is meaningful to use when categorizing people on memory performance turns out to be the color of paper. Another few ways of saying what it is that we found. It is probably not the case that the population of people using different colors of paper for the memory test are, on average, exactly the same. That's another way of saying we have rejected the null in all probability. Another way of saying what we found, it is unlikely that the differences between the means of our groups are there just because of sampling error or just because of chance. Okay? That is to say, there's probably a real difference between the mu's and not just a bunch of sampling error running around looking like an effect. Another last way of saying what it is that we have probably found is that at least one of the means was probably drawn from a population that is a different mu from the others. Now, they could all have been drawn from populations with mu's that are different from the other 3, but all we know at this point is that at least one was from a faraway mu. Okay. Here's where we run into the limitation of an ANOVA that is going to motivate us to do an extra hanger-on procedure to answer more questions about the result. Because here's the thing. We have no idea where the statistically significant differences are between the groups that we just did. Okay. The F statistic doesn't tell you. The F statistic is simply a statement about the overall model. It just tells you that there's something there. It doesn't tell you where. So what we're going to have to do is this thing called a post hoc. Post hoc is Latin for after the fact. And we're going to, after the fact, go back in and ask where the statistically significant differences between the groups were. In a study with 4 groups, there are 6 different potential hiding places for statistically significant differences between groups. Between blue and red, between blue and green, between blue and purple, between red and green, between red and purple, and between green and purple. 6 different possibilities. So what we want to do is probe each one of those 6 different possibilities with a test that says whether the difference between those 2 means on its own stands as a statistically significant difference. All right. So what we need is something that will determine what the difference is between two means. Now, you might say, we already have a procedure for figuring out whether the mean between two groups is statistically significant. Can't we just run a bunch of independent samples t-tests? And the answer is no. And here's why. That would lead to what is known as alpha inflation. Because if every single one of those t-tests carries with it an alpha of 0.05, meaning that it has a 5% chance of being declared as a statistically significant difference, but wasn't, if you ran 6 tests, each one of which came along with a 5% chance of being a false positive, you would get into an unacceptable range of probability for having a false positive. And that's just not something we can do. Okay, so what we're going to do is this thing called a Tukey's honestly significant difference. The Tukey's test takes into account how many different tests you're going to be running and keeps the alpha under control by slightly edging up the criteria you would need to declare the difference between two means to be statistically significantly different. And here's how it works. All right, you take any two means in the ANOVA, you figure out between those two means what is their, not x bar sub 1 minus x bar sub 2, not their t value, but their q value. Q is a new statistic that tells you the ratio of difference between two means to standard amount of error in the context of a statistically significant ANOVA or F test. That is 2 new statistics in 1 lecture. Yes, we're going to get a new table. You take that Q statistic, compare it to a critical value off of the Q table, and doing that comparison, you get to figure out whether that difference between those two means is in and of itself, all alone, statistically significant or not. Here's the formula. By the way, if any of you are sitting at home, you have nothing to watch, and I think NBC is out there putting all of the Star Trek online, go ahead and watch Star Trek The Next Generation. It was a great show. This is Q. That's why he's on the page, because we're getting a Q statistic. And he was like a basically godlike supernatural alien that had a fascination for dealing with humans. Anyway, that's Q. That's why he's there. Learn some culture. The formula for getting a Q statistic is this. It is the absolute value between the mean of the first group you're considering and the mean of the second group you're considering, divided by this bottom term, which is the square root of your mean squared error, your mean squared within, divided by n. We're going to talk about that n for just a little bit. Okay, but here's the nice thing. There is nothing in this Q statistic value that isn't sitting around after you've done an F test. You don't have to calculate anything new, really. That mean squared error, it's just sitting around. You've already calculated it. Okay, all of your X bars, you've already calculated them. This N is the one that you have to worry about, because this is not large N. This is not 37. This is an N necessarily for either one of the groups that you are comparing to each other. This N is basically an average number of people in each group. But we couldn't make this easy. We couldn't just get an average. We have to do not just the mean, but the harmonic mean. The harmonic mean is not just adding up all the n's and dividing by 4. What it is this. You take 4 and put it, instead of in the denominator, in the numerator. So 4 is the top here, and then you add up 1 divided by the first n plus 1 divided by the second n plus 1 divided by until you have added up 1 over all of the n's for all of the groups. That will give you what is known as a harmonic mean. So in this case, you would need to add, for the harmonic mean, right down here, 4, because there are 4 groups, divided by 1 divided by 10, 10 people in the first group, plus 1/10, 10 people in the second group, plus 1/10, 10 people in the third group, plus 1/7, 7 people in the fourth group. By the time you add all that up, you get 0.442857, divide that by 4, and you actually end up with something that is very, very close to the average number of n's. All right. In this case, it would be something very close to 9. 10 plus 10 plus 10 divided by 7. I'm sorry, 10 plus 10 plus 10 plus 7 divided by 4 will give you something that isn't quite 40, but it's not 30, but it isn't 7 either. Something close to like 9 some odd. That's almost exactly what you've got with the harmonic mean, but apparently you have to do the harmonic mean because it makes the math work for reasons that I will never even question. But 5.43 was the mean squared error that you got a couple of slides ago. The harmonic mean is this number here in the denominator. By the time you take the square root of that ratio and get a 0.77536, you can keep it, because everything in the denominator there is going to be the same for every comparison in your post hoc procedure. Okay? Nothing here in the denominator depends on which two means you're comparing. So once you get that 0.77536, you can just put it under the difference between any two of your means to get a Q statistic. What about the critical value? How do you know if your Q statistic is large? You go to a Q crit table. So we are going to use degrees of freedom within, which you've already worked with on the F table, and now K. Not degrees of freedom between, like you did on the F table, but the actual number of groups in the study, not -1. This is just to mess with you as far as I can tell. When you're using a Q statistic table, you look up K in the top row. If you're doing an F table, you look up K-1 in the top row. All right? So here's the table. There were 4 groups in our study. We had degrees of freedom within of 33, but you go back up to 30. That means that the critical value for all of our Q statistics is 3.85. If we get the difference between two means divided by 0.7758, that is bigger than 3.85, we can say that standing alone, the difference between those two groups was in and of itself statistically significant. How does that look? All right, as I said, we had 6 different comparisons to do. If I was comparing blue to red, the average of the blue group is 7.9, the average of the red group is 5.79. The difference between those two groups, and absolute value, we don't want to deal with negatives here either. The absolute value of the differences between those two groups is 2.11. When you put it over the Q denominator that we calculated 2 slides ago, you get 2.74. Compared to the critical value, does not give you a significant difference. You do that for blue versus green. You do that for blue versus purple. When you do that for red versus green, you get something interesting. The red mean was 5.79. The green mean was 8.83 for a difference of 3.04. Put 3.04 divided by the Q denominator of 0.77, you get 3.95. That is the only one of all these comparisons that gave you a Q value bigger than 3.85. So that is the only one that is in and of itself statistically significant. Red is statistically significantly different from green in the context of this analysis of variance. What that means is something very, very weird. Okay, and this is when we were reminded that we aren't dealing with real numbers here, we're dealing with statistical numbers. And statistics always means that you're taking your number with a grain of salt and realizing that there is an error term associated with it. But since only the difference between red and green was statistically significant, we are going to say a weird thing about our hypothesis test. Red is equal to purple. As far as we know, the red group and the purple group do not have different mu's based on the evidence that we've been able to collect. Purple equals blue. The difference between purple and blue was not big enough for us to declare with 95% certainty that the mu of those two groups were in and of themselves significant, different. Blue and green, we're not sure that those groups are different in and of themselves. Purple and green, we are not willing to say that those are different from each other. But the difference between red and green is big enough to overcome the amount of sampling error that we anticipate having. And so we get to declare those to be a real difference. So the red group equals the purple group equals the blue group equals the green group, but red doesn't equal green. So the transitive property of equality between mu's doesn't hold in statistics, because equality simply means we don't have enough evidence to declare inequality. but with a little bit of extra distance, we might be able to. That's what's happening here. All right. Before we go on with running everything from the beginning with another example, just to make sure that you've got it, I think it's really time for a break. Enjoy. This is one of my favorites. Well, they're all some of my favorites, but I'm especially excited about this one. Have a good run. Enjoy this, and we'll come back with another example about ANOVA.
So I threw the Senate at him. The whole Senate. True story.
Oh my God, that is so funny.
You made it come out of my nose.
Go for Papa Palpatine.
You have a collect call from
Darth Vader.
I gotta take this. Hold on. Vader, how's my favorite Sith? Whoa. Just slow down. Huh? What do you mean they blew up the Death Star? Oh, who's they? What the hell is an aluminum falcon? Okay, so who's left? Are you me? Well, where are you? Wait a sec, you've been flying around for 2 weeks trying to get a signal? Oh, you must smell like feet wrapped in leathery, burnt bacon. Oh, I'm sorry. I thought my Dark Lord of the Sith could protect a small thermal exhaust port that's only 2 meters wide. That thing wasn't even fully paid off yet. Do you have any idea what this is gonna do to my credit? Hang on, I got another call. What? I'm very busy right now. Oh, well, where are they going? Huh, all right, just get me a turkey club. Coleslaw, I guess. I'm not even gonna eat it. What are you getting? Yeah, see, I always order the wrong thing. No, I'll just stick with that. Okay, bye. What? Oh, cherry Coke. Thanks. Sorry about that. What? Oh, just rebuild it? Oh, that real f***ing original. And who's gonna give me a loan, jackhole? You? You got an ATM on that torso light bright? Now get your 7'2" asthmatic ass back here, or I'm gonna tell everyone what a whiny bitch you were about Padamame or Panda Bear or whatever the hell her name is. Oh, jeez, he's crying. Hey, come on, don't do that. Just, look, I'm just dealing with a lot of crap right now. Death Star blown up by a bunch of teenagers, I didn't mean to snap. Okay, just get back here. Okay, bye. I love you too.
Okay, so let's run another example here in order to make sure you got it. And what I'm going to look at here are 3 different groups, each one of which is having a different level of intensity and expense for advertising a product. Okay, so the independent variable here is going to be the type or intensity of advertising campaign. That is the thing that is going to determine our groups. The levels of those groups are low. If Juul is trying to get you to smoke, or vape their stuff, they could just give free product. They could also give free product and free food, like pizza. You know that if you have a student club or something that you want people to show up for, they could get free pizza and people will have a tendency to show up. But if you really wanted to go all out, you could give away free Juul pods, you could give away free food, and you could give away a pair of Yeezys, okay? Give away some free Nikes, all right. It would be very expensive, but getting somebody hooked for a lifetime on Juul pods actually pays quite handsomely. And so maybe it's worth it. All right, so the dependent measure here will be the amount of vaping that people do. That is going to be operationalized. That is going to be measured by saying the mean number of pods that a person used in the week following a 6-week advertising campaign will determine their degree of use. So they do this advertising campaign, they give away whatever they're gonna give away to these people for 6 weeks, then they let them go on their own and they see how much they smoke in the week following that. Here are the data. There were 5 people in each group. People who just got free Juul pods smoked 2, 3, 1, 3, and 1 in the following week. That was an average of 2. The people in the moderate, people who got free pods and free pizza, smoked 8, 4, 6, 8, and 4 pods the following week. And the people who got free product, free pizza, and free shoes smoked 9, 5, 7, 5, and 9 pods, and that was an average of 7. So X bar sub 1 in the low group is 2, X bar sub 2 in the next group is 6, and X bar sub 3 in the highest group was 7. Those are our 3 X bars. Since there are 3 groups, we gotta run an ANOVA. So what we're interested in figuring out is whether the difference among 2, 6, and 7 is enough to overcome the differences that we are experiencing within those 3 groups. All right, so K is equal to 3. Our sample sizes are all the same, 5, 5, and 5, and that makes 15 people total in the study. So N equals 5 for all the groups, but big N equals 15 for the whole study. Get yourself all set up to make your conclusions. You can do this right away. If I set alpha equal to 0.05, I can already, without doing anything else, look up my F crit. I can look up my critical value. Go to the table, look for K equals 3, but that's not what we look for in the F table. We look for K minus 1, the degrees of freedom within. So we're going to go across to the 2 column. And then for degrees of freedom within, there were 15 people in the group, but there were 3 groups. So 15 minus 3 is 12. And we will look for the intersection between 2 and 12 on the F table. That gives us a critical value of 3.89. All right. Then we take up our steps in the computation of ANOVA. We get a grand mean. We can then get the group means. We already have the group means, but we'll have to get a grand mean. We'll get the sum of squares within. We'll get the sum of squares between. We'll put each one of those sums of squares over their relative degrees of freedom to get mean squared between and mean squared error. We'll then take those, put them in a ratio to get F, compare it to a critical F value, and then do post hocs. All right, so first off, the grand mean, that equals 5. We could take all 15 people, add them up and divide by 15. Another trick, as long as there are an even number of people in each group, you can just add the group means and divide by 3. Here's how to get the sum of squares within. This is basically a sum of squares for each one of the groups. If you want to take a look at the details, pause it here, okay? But you'll figure out that sum of squares for the low group was 4, sum of squares for the medium group was 16, sum of squares for the high group was 16. Add them all together and you get 36. That is the sum of squares within. For the sum of squares between, tricky again, make sure you pay attention. The grand mean was 5. The mean of the first group was 2, so 2 minus 5 equals -3. Multiply that by itself, that is to say square it for a 9, and then multiply it by 5, which was the number of people in the first group, and you get a 45. Same thing for the second group. The difference between 6 and the grand mean is 1. 1 squared is 1, times 5 is 5. For the third group, they had an average of 7. The grand mean is 5. 7 minus 5 is 2. 2 squared is 4. Multiplied by 5 people in the third group gives you 20. Add those all up, you get a sum of squares between of 70. So the hardest parts are done, sums of squares within and sums of squares between. Now we need to get them in a place where we can get the mean squares. This leads us to something that's actually going to be very useful when you're navigating SPSS. SPSS will give you the results in something that looks like this. This is called an ANOVA summary table. They will start off with the sums of squares right here. They will then give you the degrees of freedom right here. Putting this number over that number will give you the third number. 70 divided by 2 equals 35. That's the mean squared between. 36 over 12, that is the sum of squares within over the degrees of freedom within, will give you the mean squared within, or the mean squared error. Putting 35 over 3 will give you the next column, the F statistic, which in this case is 11.67. Next, it will give you what SPSS will call significance, SIG, but we understand as the probability of having observed that result if all the groups were actually at the parameter level equal. If that number is very small, then it is a statistically significant result. If that number is large, it is not a statistically significant result, and the borderline between large and small is alpha, in our case, 0.05. So if that number is less than 0.05, then you have statistical significance. If that number is greater than 0.05, you don't. Since the criteria for getting statistical significance here was 3.89, and we have far exceeded 3.89, then we know that the probability of getting that result was very small if the null was true. So since our F statistic outpaced the critical value, we know that P is less than 0.05. We're going to reject the null. Post hocs look like this. What is the Q critical value? Well, you go to your Q critical table, you say 3 groups, 12 degrees of freedom within. The Q table says you have to exceed a 3.77 for a comparison in order for that comparison to be statistically significant. What are the Q statistics for our 3 comparisons among our 3 groups? Much easier. Since you only have 3 groups, you only have a comparison between 1 and 2, 2 and 3, and 1 and 3. Not 6 comparisons anymore, only 3. The low group versus the median group gives you the average of 2 minus the average of 6. That's a -4, but take the absolute value, it's 4. Divide it by the mean squared error, which, nice enough, we were keeping this simple, was 3, divided by n. The average of the n's is 5. The harmonic mean of 5 and 5 and 5 is just 5, just like the average of 5 and 5 and 5 is 5. So the denominator here is going to be the square root of 3/5 every single time. If you put 4 over the square root of 3/5, you get a 5.16. If you put, let's see, low versus high, that is the difference between 2 and 7. So if you put a 5 over the square root of 3/5, you get a 6.45. But if you put the median versus the high group, that is to say an average of 6 and an average of 7 divided by the square root of 3/5, you get a 1.29. These 2 comparisons are significant because they're greater than 3.77, but this comparison is not significant because it doesn't get to 3.77. What that means in practical terms is that if you're just giving away free Jewel pods, but you have the option of giving away free pizza as well, that will give you a statistically significant bump in consumption of your product. But if you're already giving away free pizza and free Jewel pods, throwing shoes into the mix doesn't give you a statistically significant bump in product consumption, and so you might want to save on your advertising budget and withhold that final last level of investment. Okay, so that's ANOVA. We will come back together on Thursday during class time for you to take a look at your in-class assignments and work in ANOVA out on your own and ask me questions at that time. Again, that is the absolute best time to ask me questions. Please be there if at all possible in order to work through that assignment on your own. And I'll see you then. Take care.